So good morning all. Today we will be discussing the hashing algorithm SHA-256. SHA stands for Secure Hash Algorithm. Okay. So it is there are different variants in the SHA family, and it is usually based on the McLeod-Lampard scheme. Okay, we will see how it is working. We have generally seen that we describe your hash algorithm in the generic term as small h is the output, the hash that is generated from the algorithm, which is equal to h, the capital H is the hashing algorithm that we are deploying to a message M. We have seen few requirements for this H. First thing is it should be able to handle variable size input, but it should be able to produce a fixed size output. Third is it should satisfy the one-way property, meaning given the output, it should be computationally infeasible to find the input. Then it should be collision resistant. These are the requirements we saw for designing a hash algorithm. In hash, we use hashing techniques to achieve the security service of integrity. Okay. And hash is a one-way function. It is computationally infeasible to get back the message from the output hash. So SHA-512, it depends on the naming standard is based on the output bits that is generated. If the output that is generated is small h, if the small h is going to be 128 bits, it is known as SHA-1. The output that is being generated, if it is going to be 256 bits, then it is known as SHA-256. And if the output is going to be 512 bits, it is known as SHA-512. So the output 512 is called as your hash code. So in this algorithm, capital H is your SHA algorithm, M is your variable size input that you're going to process, and the output is going to be 512 bits. Okay, so these are the characteristics of the various variants in the SHA family. So you have SHA-1, SHA-224, 256, 384, and 512. 512 is the one we are going to discuss. Okay, so these are the various characteristics against which we need to understand this algorithm. Okay, so what is the maximum input that it can process? It can process up to 2 power 28 minus 1. So this is the capability of SHA-512. And the message that is received, it is split into blocks and it is processed as blocks. Okay, what is the block size here then? It is 1024 bits. So whatever be your input, it is divided into chunks of 124 bits, and each chunk is processed one block at a time. The output that we are going to generate, the hash code, is also known as the message digest, which we have discussed. Okay, so the message digest, the size is going to be 512. That is the output. The output that is generated by this algorithm is known as message digest. That size is going to be 512 bits. The number of rounds that is used here is 80 bits. Okay, and then we will use something known as words here. Okay, SHA makes use of words. We will see what are words, and each word is going to be 64 bits. Okay, so for each round, total there are 80 rounds. Each round will make use of a word. So there are totally 80 words, each of size 64 bits that will be generated. So these are the characteristics which we will be discussing. Okay, so again in summarizing, the plain text is split into blocks, and each block is of size 1024 bits. And total number of rounds that is utilized in SHA algorithm is 80 rounds. Inside each round, we will make use of a word. It is known as the keyword, or mainly W. We will use it as W. This W, we are going to generate it from the plain text, from the original message. And each keyword is going to be 64 bits. Totally, we need 80 keywords, 80 W. So W will be from W0 till W79. W0 till W79, and each will be 64 bits. Okay, and each round will make use of a constant which is expressed in hexadecimal, and those constants will be given to us. Okay, and the intermediate output and the final output will be stored in buffers. So what is the total size of your output? It is 512 bits. Okay, and the size of each buffer is going to be 64 bits. So totally we need 512 divided by 64, that is 8 buffers. So we will be making use of 8 buffers. What is the purpose of the buffers? To store the intermediate results as well as the final output, which is the hash code. Each buffer will be 64 bits and there are totally 8 buffers. So 8 into 64 will give us the output of 512 bits. Okay. So your SHA or any hashing algorithm will work based on the chaining process. So in chaining process, what we do, the output of the previous block is given as input to the next block. And in the last block, we get the hash code. And usually the first block will not have any uh, content. So we will fill it with an initialization vector. Okay, we will see how we are going to fill the initialization vector. Okay, so this is the chaining process in SHA512. So we take a 512 bit initial value, we process the first block, and we get the intermediate result. This intermediate result is given to the next block to the compression function, and the block it produces the next intermediate result, and so on we process until we have processed the last block. So this is our entire message, and we have divided the message into chunks of 1024 block or 1024 bits each block. So totally here there are n blocks, and we are going to process that. Okay, we will see how we are going to process. So the very first step is given an input divided into blocks of 1024 bits. And how are we going to do the input processing? So the input processing is we have to know what is the original size of the message. Based on that, we will do padding. Okay, so that we are able to fit the entire message, overall message into a multiple of 1024 bits. Okay, so that is the first thing that we have to do. So first, what we have to do is we have to first find the original plain text. Okay, the original message, its corresponding length. The first requirement is the original length should be less than 2 power 128. So as per this characteristics. Okay, as per this characteristics. So the original length should be less than 2 power 128. That is the first requirement. Then we take that original message. We express this length in a binary notation using 128 bits. This is the second step. The first step is we need to find the length of the original message. We ensure it is less than the processing capability of the SHA512 algorithm. Second step is we express the length, original message length as in a binary notation in a 128-bit notation. Then we do a padding to adjust the variable length so that this block becomes a multiple of 1024. If the entire size was say 3000 or something, the first block would be 1024, second block would be 2048. From 2048 till 3000 odd, whatever was the remaining, we have to do the padding appropriately. How do we do the padding? We have to take 1 followed by multiple zeros. So this is how we will be doing it. So before we create the digest, we need the length field to be computed, which is the original input message length. So we express that in 128 bits. That is the length of the original message before padding. That is the length of the original message, which is 128 bits. Then we need to pad the original message so that it becomes the length of the 1024. So how much we should pad, that we have to do based on this formula. So that this 128 is the length of the original message which we are expressing. This is the original message, and we need to pad something suitably so that this entire bunch becomes a size which is a multiple of 1024 so that it satisfies this equation. So to find padding, we take the terms to the other side and we take a minus mod and we solve it. We'll just take a simple example. Assume my original message is 2590 bits. Then when we want to find what is the size of the pad, so here we usually have 3 components. Okay, so we have 3 components. So this last component will be your 128 bits to denote that it is my length. And then here I have my original message. Okay, 2590. Now I need to add something so that this entire bunch is a multiple of 1024. So what we do, we take minus 2590 and minus 128 mod 1024. We add them, we get minus 2718 mod 24. We simply solve this and we get 354. So totally 354 has to be padded. How do we do the padding? So it should be 1 followed by multiple zeros. 1 followed by how many zeros? 1 should be followed by 353 zeros. So this is how we have to do the padding. So this is the now this bunch. This bunch now has to be split into blocks of 1024 bits. Okay, so we divide into corresponding blocks of 1024 bits. This is how we split it. So first step is input processing. In input processing, we take the message, we find its length, we express it in terms of 128 bit length. Then we subtract both and we find how much should be added to do, how much should be padded. The padding is done by a 1 followed by that many zeros. This is the entire bunch. We then split it into blocks so that we are able to process each block at a time. Now, these are some questions which we commonly ask about the padding. Okay, if the given input message, if I'm going to process my message, the original message say it was 2048, which is actually a multiple of 1024. Now, should I do the padding? Yes, because the original message is 2048, but I need the receiver should know the length of the original message, whether there was original padding or not. So we need to insert the length of the original message. So we have introduced 128 bits again. So this makes the original message now go out of sync with the multiple of 1024. Correct? So then we have to do the padding. Then what should the second and third question is, what should be the minimum number of bits that can be padded and what is the maximum number of bits that could be padded? Okay, so suppose the original length of the last block, the original message say it was some number, some odd, and the last block had 896 bits. Okay, the 896 bits means, let's process it. Okay, so it should be 896 minus 128 and we process it. Okay, so totally we need to add at least this many bits so that we need to do the padding as 0. Okay, no padding means then the block should be at least 896 bits. For maximum length, what should we do? Then the maximum length should be, we should be able to pad at least 897 should be the maximum bits to complete. Okay, now we are going to do the formal processing of the algorithm. Here, SHA works on words. Each word is going to be 64 bits, meaning, say we will take one block at a time. My one block, the current block which I'm processing is going to be 1024 bits. This block I'm going to split into 16 words. Each word is going to be 64 bits. Okay. Now what are we going to do with it? As we discussed here earlier, we said each round, okay, there are 80 rounds, and each round is going to make use of a keyword W, which is going to be 64 bits. Now, this is the point that we are going to discuss. How are we going to generate 80 different words to be given as input to the 80 rounds? And each word has to be 64 bits. Okay. So whatever is in the current block is 1024 bits. That we are going to split and form the first 16 words, because 1024 divided by 16 will be divided by 64 will be 16. Okay, so word 0 to word 15 will be obtained from the given current block. Okay, the current block is split into 64 chunks. The first chunk is going to be word 0, second chunk is going to be word 1, and till the last chunk will be word 15. But we still need few more words, because totally we need 80 words. Okay, how are we going to generate the remaining words? For that we will follow an operation. Okay, so again another diagrammatic notation. The given block we are going to split it into 16 words. Each word is going to be 64 bits. Each word is going to be 64 bits. So this is my current block. I am able to generate the 15 words as such. From the 16th word till the 79th word, we are going to follow this process to generate the words. Based on that, we are going to make use of these words to generate the remaining words based on this formulation. Okay, so in this diagram is going to explain us from the given input sequence how are we going to generate the remaining words. Okay, so to generate a new word, say WT, we are going to follow this formulation. Okay, it is going to be sigma 1 word, the corresponding T minus 2 plus word T minus 7 plus sigma naught word t minus 15th index plus word t minus 16. Here the plus is going to denote addition modulo. Okay, that is the operation used here. What is the sigma 0, what is the sigma 1, and what are the internal operations involved, we will see. Sigma 0 of a particular element is nothing but we are going to do a right rotate by 1 bit plus a right rotate by 8 bits. Then we are going to do a shift left n bits with padding by 0 on the right. So this is the sigma 0. In sigma 1, what we have to do is we have to do a right rotate by 19 bits. Then we have to do a right rotate by 16 bits. Then we have to do a shift left by 6 bits with padding by zeros on the right. So in this way, we will be able to generate the 16th word, then the next word and next word and so on. So this is the way in which we are going to generate words to be given as input to the each round algorithm. Each round takes one word and the word is going to be 64 bits in size. The first 15 words we will the first 16 words we will directly generate from the given message by splitting it into chunks of 64 bits. The remaining words, word 16, word 17, word 18, we will be following this notation. Okay. So this is how the simple example. If I want W60, then word 60, the formula is we have to you have to substitute T here as 60. Okay. So it should be sigma 1 of WT minus 2. We will be this term comes first here, then formulation. Then we are going to process here. Okay. Same methodology, but they just process it here. Now we will go on to understand the message digest. What is message digest? It is the hash code or the output. The output means the outputs are usually stored in the buffer. We said, right? The buffer is going to be 8 words. Each buffer is going to be 64 bits. That is going to be 512 bits. That is 8 into 64 will be the total size of the message digest, or the hash code will be 512 bits. We said in this training process, the initial round will not have any content. So we need to fill this buffer with the message digest with some initial values, with some initialization vector. So here in SHA512, we make use of some constants for initialization, which is given like this. So we initialize the buffers. The buffers are given as A, B, C, D, E, F, G, H with some values from the hexadecimal given as such here. Okay, so these are the values that we are going to make use of for initializing the 8 buffers. Now we are going to do the processing of your SHA algorithm. So this is your entire message. This was the first step that we discussed. This was your entire message. We found the size L and we expressed that L in 128 bits. Then correspondingly we did the padding. This was step 1. So then we were able to formulate totally n into 1024 bits. That was the total size. Then we were able to get blocks of n. So we had M1, M2 till Mn blocks. Each block was 1024. Now we have initialized the message digest with the given hexadecimal values, which we are going to call as H0. This H0 and the first block M1 will be given as input to the F function. Totally, the F function will have 80 rounds. Okay, will have 80 rounds, and after processing, that will be given. Okay, so the current input is done processed here along with it to produce the next round output, and this step keeps on continuing until we generate the final hash code. Okay, so now we have seen how to split the message, how to do the padding, how to do the length computation and form each 1024 bits. Then we have initialized the IV vector. Now we are going to see how we are going to process one block at a time. Processing of SHA512 bits, one block at a time. And within one block, there is this function which is going to do 80 rounds. Okay, that is known as the compression function. So this compression function usually takes 80 rounds, and each round takes 3 inputs. One is the Q word that we discussed, the other is the K constant, and the intermediate digest. Okay, here the plus indicates always here the addition modulo 64. Okay, so one round, one block of processing. So one block here denotes this part of the diagram. Okay, we are going to take this one block and we are going to give it to this F function. and we are going to see what is going to happen to produce the output here. Okay, so this is the thing that is happening. This is your M, that is your 1024 that we receive. This is the H0, which is 8 buffers. Each buffer is going to be 64. Totally we have 512. Okay, so then there are three inputs I said, right? So from the message we will generate 80 words. The first word is given for the first round. The second word is given for the second round. The teeth word is given for the teeth round. And the last word is given for the last round. And there are 80 constants which we denote as K0, KT, K879 which is used. Okay. And we are going to do, we will see what is happening inside each round. So what is this diagram? This is, we take one block and we are going to process that one block to convert this Hi minus 1 to Hi. Okay, we are going to convert this intermediate output to the next intermediate message digest output. So to do this process, this takes three inputs. One is the M, the other is the K, and the previous H0. From the message, we are going to generate 80 words and we need also 80 constants. Now we will see what is inside each round. Okay, understood? So the same in a better way. Okay, we get the results of the previous block or the initial digest, and we are going to get the values for the next block. We are going to make use of words from the corresponding block and the constants. Okay, what we are going to process. After the 80th round, the previous thing is added here using your addition modulo, this part here. Okay, the previous round is added to this output using addition modulo, and that output is only going to form this round intermediate hash code or message digest that is generated. Okay, so this constants K0 till K79 are given here. Okay, this is based on finding the cubic root of different prime numbers, and they are given here. Okay, so these are the values of the constants K0 till K79 that is utilized in your SHA512 for each of the 80 rounds. Now we will see what happens inside each round. We are going to expand and zoom in on what is going to happen on each round. Okay, so in each round, what is going to happen? We are going to give, we are going to take this A, B, C, D, E, F, G, H from the previous block, and we are going to generate the A, B, C, D, E, F, G, H for the next block, making use of W0 and K0. Let's see what happens. Okay. So now a few contents are just given to their adjacent people. For example, A becomes the new B, B becomes the new C, C becomes the new D, E becomes the new F, F becomes the new G, G becomes the new H. Okay, and the A and E are something different. There is some computation followed for finding the new A and the new E, which we are going to denote as X and Y. Okay, here X and Y. This X, what we compute using this logic, will be the new A. This Y, which we compute using this logic, will be the new E. Okay, what X computes is, it is going to take three inputs, A, B, C. A, B, C. Okay, here, this we are going to call it as majority. We'll go step by step on each block. Okay, majority is A, B, C. So here, it is going to take the majority of the 3 bits that is given. If all the 3 bits are 0, then you get 0. If all 3 bits are 1, it gets a 1. So at least 2 should be same number to get the majority. If at least there are 2 ones, you get a output as 1. If there are 2 zeros, you get an output of 0. So majority should be at least 2, correct? Out of 3. So you take these 3 elements and you find bitwise between them and you find the majority. And then you do a rotate here. Here rotate by the corresponding bit. The bit position will be specified. Okay, and you do a addition modulo. Always here in this SHA plus denotes the addition modulo 2 power 64. Okay, this is called as a mixture 1. This mixture 1 is again added with this output to get the A. Okay, here in this what you're going to do is you're going to take H, E, F, G. You're going to take H, E, F, G. What you're going to do is On EFG, they are going to do a conditional. What is the conditional is, if it is going to be X, E, if E is going to be true, then it will return F. If E is going to be false, it is going to return G. That is how it is going to be conditional. Conditional on X, Y, Z. If X, then Y. Otherwise, if it is not X, it's going to return Z. Okay. Then they're going to rotate it by E. They're going to do additional modulo. Here, they are also going to do additional modulo using these 5 terms. The H, this conditional operation, this rotation by E, the word generated for this round, and the constant that is used for this round. All these are done for an additional modulo. That intermediary output is taken as mixture 2 output, mixture 1 output, and it is added to get the output for the new A. This output is again added with D to get the output for E. Okay, so this we will explain in another diagram, same stuff, but in a formal way. This is the diagram in the textbook, and this is the diagram which explains it better. Okay, so we are going to use this conditional function and majority function to compute the next round. So only A and E are updated. The other elements are going to be the previous elements. Okay. So what is this majority function? What is this conditional function? What is this rotate function? So in majority function, it is going to be, you're going to find the majority between the 3 elements. Suppose say it is A, B, C. Okay. Suppose your C and your A were ones. Your A, B, and your C. Assume those, out of these 3, we need to find the majority. We'll assume that A is 1, B is 0, and C is 1. We will check whether this returns 1. A and B will be 0, 0. B and C will be 0. C and A will be 1. So we will just do the next one. 0 XOR 0 is 0. 0 XOR 1 is 1. So it returns the majority. Conditional will return, it is based on your E. If E is going to be true, it will give us F. If it is E is not going to be true, it is going to give us G. Okay, then there are 2 rotate operations which we saw here, right? We saw rotate E, rotate A, and rotate E. Rotate A and rotate E. How much we have to rotate A? How much we have to rotate E? Okay, so here it is rotate right by 28 bits, and then rotate right by 34 bits, and then rotate right by 29 bits. Everything A, we are going to rotate it correspondingly, then we are going to take a XOR. Then E, we are going to take, we are going to rotate right by 28 bits. We are going to again rotate E by rotate it right by 34 bits. We are going to take E, we are going to rotate it right by 29 bits. All those values we are going to XOR it, and that is the answer that we are utilizing. Okay, so these are some example homeworks which we will again expand on, and we will also solve one example for solving one round SHA-256 in the next class. Okay. So please ask me doubts. Where you want me to